This video is about systems of linear equations in two variables. This is a review in that we are in the context of an intermediate algebra course, and typically these topics are introduced in a class before this, but there is often some overlap in when and how these topics are discussed. We'll start with an example where we want to review the substitution method of solving a system. This system of two linear equations begins as follows. Our first equation is x minus 3y equals 3. Our second is 3x plus 5y equals negative 19. Now, as you may recall, for the substitution method, the first step is to solve for one variable in either equation. We want to get either x or y alone in either one of these equations, and there's some freedom there to pick. So why don't we make our lives as easy as possible and pick on this first equation, which almost has this x alone. It's just one quick step to get that. So we're going to go ahead and just pull that first equation off to the side. It was given as x minus 3y equals 3, but to get that x alone, we could simply add 3y to both sides. And this will give us x alone on the left side equals 3 plus 3y on the right side. So remember, step one in substitution is to get one variable alone in either equation, and we have that now. So we know x is equal to this 3 plus 3y, or you could write it as 3y plus 3. The order of those doesn't matter. But that expression now is going to be plugged in for x in the other equation. So now I'll take the second equation and recopy it, except we're going to replace x with now what we're saying it's equal to. So instead of 3x, as in the first term of the second equation, I'm going to put 3 and then a set of blank parentheses. And in those blank parentheses, we're going to put what we've already decided or discovered x is equal to, which is this 3 plus 3y. Then we continue on with this second equation. So we'll say then plus 5y equals negative 19. And now the whole point is that we have an equation with only one variable. They're all y's, and we can solve for that variable. So we'll go ahead and distribute the 3 to get 9 plus 9y plus 5y equals negative 19. And then we can combine like terms. At this point, we're just doing the typical equation solving steps. The 9y plus the 5y will give us a 14y, and so 9 plus 14y equals negative 19. Then we'll go ahead and subtract 9 from both sides, which will give us 14y equals, and then on the right side we have negative 19 minus 9, that'll be a negative 28. Then we can divide by 14 on both sides to get the y alone, and we'll end up with y equals negative 2. Now, once you find that value for y, as we just did, we can go back to the equation we had solved for x in the beginning and plug in now the value for y that we've discovered of negative 2. So we can now say that x equals 3 plus 3 blank instead of y, and in the blank we'll put negative 2, which we just found y to be, which means x equals 3 minus 6, which means x equals negative 3. So we'll put this all together as an ordered pair to finish, x comma y, so negative 3 comma negative 2, and that will be the solution to our system. Let's try another example where we will review the topic of solving by addition, or it's called elimination. Different authors will call it different things, but it's the same method. And in this method, we want to multiply entire equations by non-zero numbers to get the coefficients to be opposite and therefore cancel. So this may start to look familiar. Again, we're just reviewing this topic. Chances are you've already seen it at this point sometime before. Now, you'll notice the coefficients for the x's are 1 and 3. For the y's, they're negative 3 and negative 9. Now, we need to get a pair of those to be opposites, and it doesn't matter which pair. So if I were to, let's say, pick on the x coefficients, the 1 and 3 that we begin with here, I'd want those to be opposites, and we'd use the least common multiple of those numbers for that number with opposite signs. So the least common multiple of 1 and 3 would be 3, which means I want these coefficients to be one of them 3 and one of them negative 3. Now notice the second x coefficient is already a positive 3, so why don't we worry about getting the first one to be a negative 3, and we can multiply entire equations by non-zero numbers to do this. So it would make sense to multiply that first equation by negative 3, because then negative 3 times the 1x would be a negative 3x, and that's what we want. Now we have to do it all the way down the equation. So we're multiplying by negative 3 all the way through, so then we'd have a plus 9y, and then that's equal to a positive 18. Now the second equation we actually don't want to change. I'm not going to multiply it by anything because we already have the 3x that we were anticipating canceling there. So I'm just going to copy the second equation down. Now once we have the opposite coefficients, we simply add down the like terms. So negative 3x plus 3x will cancel. That's the whole point of doing that. But notice in this example that the y terms now also cancel. The plus 9y minus 9y. Sometimes it happens that upon trying to get a certain variable to cancel, you end up canceling both of them. That's okay. Let's see what happens next though. So we have 0 on the left side, everything canceled out. On the right side though, we'll add the 18 and 9, the constant terms on the right sides of the equations here, and get 27. But in a case where the variables all disappear and what you're left with is not true, which is the case here, 0 does not equal 27, that's a case of no solution. You may recall this from learning this topic in previous times as well. So the symbol for no solution is a 0 with a slash through it, but I'll also write here no solution, just so we know that that is technically our answer for this particular system. Now you may recall, just as a means of review, that in graphing this would mean that they are parallel lines, they do not intersect. Let's try another equation. This time it says solve using any method, so we've already reviewed substitution and elimination. We could pick either one for this one. Now this system begins, and of course it has fractions, which we should pay attention to here. The first equation is 1/16 x minus 3/4 y equals negative 1. The second equation is 3/4 x plus 5/2 y equals 11. Now, as you may be pretty familiar with at this point, usually students will kind of panic when you see all these fractions floating around, kind of thinking, well, okay, I know the substitution method, I know the elimination method, but the fractions just freak me out. So instead of freaking out about the fractions, let's actually get rid of them by clearing them first. So I'm going to suggest that our first step should be to clear the fractions, which, interestingly enough, actually involves the process of the elimination method of solving a system. Okay, what I mean is, to clear fractions, as you may know, you have to multiply by the common denominator of all of the fractions in the equation all the way through. Well, if you look at the first equation, the denominators were 16 and 4. The common denominator of those would be 16. So I'd want to multiply the entire equation by 16. Now, if I do that all the way across, of course, I'll end up with just x, and then minus, and then 16 times 3/4. Really, the 16 over the 4 would reduce to 4. So I should end up with a negative 12y equals, and then all the way across I'll have a negative 16. That's just 16 times negative 1. So that's clearing the fractions in the first equation. If you look at the second equation, with those denominators being 4 and 2, the LCD of those would be 4. So we're going to multiply it by 4 all the way across. That will give us a 3x plus a 10y equals a 44. Now, at this point, remember, we were just trying to clear the fractions. That's all. And notice we're not really ready to eliminate anything. At this point, if it says using any method, you could really take your pick. Clearing the fractions doesn't really commit you to one particular method. So it would be just fine to use substitution for the rest of this problem. In which case, I would probably pick to get that x alone in the first equation. Remember, you're trying to solve for one variable in the substitution process first. But you could also use elimination to go from here, noting that the x coefficients are almost opposites. with one quick step we could fix that. That's probably what I'll choose to do here, though again it doesn't really matter which method you use at this point. So if I were to multiply the top equation by -3, notice the motivation for doing that is to get these x terms to cancel in the elimination or addition method, and multiply by -3 would do that, because then I'd end up with a -3x and then plus 36y equals 48. Now, remember, we're trying elimination here, in which case I don't want to change the second equation because these x's are now already set to eliminate. I'm just going to copy it down. The second equation is 3x plus 10y equals 44. So now we'll go ahead and add down to combine these like terms and eliminate the x's. That was our whole point. That gives us now, if we add the y's, we have a 36y plus 10y, which would be a 46y. Equals, and then we have 48 plus 44, which would end up being a 92 on the right side. We'll divide by 46 on both sides to work on getting this y variable alone. So we have y equals 92 over 46, which happens to be 2. All right, now that we know what y is, we have to go back and find x. But as you're familiar with in the elimination process like this, you're now going to take what you know y to be, which is 2, and substitute it into another equation. Now, typically you'll go back to one of the original equations in this elimination process, but since the original equations had those nasty fractions involved, we're actually not going to do that. Rather, we're going to go back to one of the equations where we had already cleared the fractions. I'm just going to pick on the first equation after clearing the fractions, which ended up being x minus 12y, but instead of y, I'm going to put 2, since we now know that's what it is, and that was equal to -16. And now we can solve this equation for x, which will give us what we need to finish this off. So we'll say x minus 24 equals -16. Of course, we'll add 24 to both sides, and end up with x equals a positive 8. Which means we could finally or write our final answer as the ordered pair 8, 2 for this system. Let's try another example where we're still in the context of using either method we want, substitution or elimination. And in this one, the system begins as follows. The first equation is 2x minus y minus 5 equals 0. And the second equation is 10 equals 4x minus 2y. Now, what you'll probably observe right away is that these equations don't seem to be in the preferred order of, like terms lining up vertically or equal signs lining up vertically. So we're actually going to rearrange these terms before we do much work with them. So let's rearrange first. And to do that, we'll simply try to get them lined up so that it's a more familiar setup where you have maybe the x's lined up vertically, then the y's, then the equal signs. That's a typical order you might see. So you can just do some simple algebra of moving things around to get this. In the top equation, we're going to leave the 2x minus y as it is, but we're going to go ahead and add 5 to both sides to get that -5 moved over, which would now become a positive 5 on the right side. Then, for our second equation, we'll do a similar kind of just moving things around, although you could just kind of flip it all backwards. It's 10 equals and then something that looks how we want it. So I'm just going to copy the 4x minus 2y and then say equals 10. I'm just kind of rearranging which side the equals 10 is on. And this is really not even a major algebraic step. It's certainly legal to move things around like this. Once now arranged better, we can focus on trying to use a method to get things eliminated. In fact, let's pick elimination for this one. The numbers are fairly set up for that. I could try to eliminate something by multiplying the top equation by -2, all the way across, of course. That would result in a -4x and then plus 2y equals -10. And then we'll just copy over this second equation. We don't want to change it so that we can already have some things eliminating. That'll give us a 4x minus 2y equals 10. Now, as you go to eliminate, remember, you might have been focusing on the x's or the y's in particular to eliminate them, but that one step we just did would actually eliminate both variables, giving us a 0 on the left side. And then on the right side, we have negative 10 plus 10, which is also 0. So when you end up with variables disappearing like this, but an equation that's true, such as 0 equals 0, this is a sign of infinitely many solutions. And the way we typically write them in this context, though you may see some differences in the authors on this, is we're going to use set notation where we have these curly braces. And our solution is, we don't say all real numbers because that's not true. Rather, it's all coordinate points of the form x comma y. So we're going to write x comma y, where, and then we put this vertical divider bar here, and then after it we put either one of the original equations. It does not matter which. So I'm just going to copy down the first one, which was 2x minus y minus 5 equals 0. And then we close up the curly braces. So again, this is called set notation. It's really just one of a couple different ways you might be able to write out or express the infinitely many solutions that a system like this has. But it's one valid way of writing this out. Now that we've reviewed, at least in this topic or video, substitution and elimination, there are other methods. Well, there's one other method of solving a system that we did not review yet, or at least use to solve an example, but I want to discuss it. So there's also a method called solving by graphing, and it is often not the best method because it might depend on a hand-drawn graph, which is usually not that accurate. But it's often a valid method, maybe with a computer system or calculator. Let me just review some basics of it, and that is, if you have one solution, as we've seen in some examples above, it's usually some kind of x comma y coordinate, and that would be where the lines intersect once. Okay, so these are systems of linear equations at this point. And so you would see the lines crossing or intersecting at one point. That point is the solution. So any system above where we've had one point as the solution would be just that. The lines could be graphed and you'd find them intersecting at that point. But you could also get a scenario where there's no solution. And in this scenario, you would have parallel lines that don't intersect, but they're different lines. So of course, if the solution is where they intersect and parallel lines don't intersect, then you would expect that to be the case where there's no solution. Or if you had, thirdly, the case where you had infinitely many solutions, which we've now represented using set notation, this is where both equations are actually the same line, and so they intersect everywhere. The visual of this system would be actually looking like one line, but it's really two lines, one right on top of the other. So this is just a little review or note about the graphical implementation of these systems, though in this topic we simply use the algebraic methods of solving them.